In this work, we present a system of transfer learning for genetic programming, which uses a set of deep learning neural networks to predict portions of the code. We then use a standard genetic programming algorithm to complete the rest of the program. The code fragments deployed by the neural network are extracted from programs previously generated by the GP algorithm, allowing transfer learning. Each time a program is generated by the genetic algorithm, a set of code fragments can be extracted. We extract fragments which form logically consistent elements, by avoiding selecting fragments which feature variables which have been written to by lines of code not contained within the fragment. These fragments can contain loops and conditionals, and aim to capture a part of the program which can be usefully transferred to another. Using a code fragment, we can train a neural network to recognize programs which have a high probability of containing that fragment. The neural networks perceive the programs in the form of examples of input-output sets, and our goal is to train a neural network to recognize which of these I/O sets are generated by programs with the neural network's given fragment, and which are generated with programs without it. Training corpora are generated by first establishing two sets of programs, one of all the programs generated so far containing the fragment, one with all the programs the GP has generated without it. To grow these sets, we simply apply our existing genetic mutators on population members of these sets. Two parents are chosen at random, crossover applied, and then mutations. These children are accepted if they meet two requirements. Firstly, that they either contain or do not contain the code fragment, depending on which corpus they are intended to belong to. And secondly, whether they differ behaviorally from programs already present in the corpus. To determine behavioral distinctiveness, we simply feed all programs a fixed input, and discard those whose output matches that of a program already present in the corpus. What this produces is essentially a random walk through program space in the vicinity of programs which have been generated by the GP in response to a user specification. We aim to, by this process, sample a set of programs which are of higher usefulness to our users than those which would be sampled by uniform selection from the entirety of program space. Each fragment has a neural network generated for it, which attempts to recognize it. Some fragments do not, by themselves, have sufficiently recognizable effect on the program's behavior for a neural network to gain an above-chance accuracy. These can be discarded at this stage. Those which show an ability to be recognized are kept in the pool along with their associated network. A simple example is the fragment loop. Programs which contain a loop may feature outputs which are often highly recognizable. While a program which outputs an array of integers could plausibly fill an 8-length array with non-zero values, the balance of probabilities is that if a program outputs multiple values, it contains a loop. Conversely, if a program only outputs a single value, it is far less certain that it contains a loop, and so our probability estimates can approach the marginal value, in our case 0.5. When a user submits a new I/O specification for the GP to solve, all neural networks can be presented with this I/O behavior, and their estimates as to the presence of their particular code fragment can be obtained. From these, we employ a heuristic weighting function to select a single fragment. This heuristic attempts to maximize the particular network's reliability and also the degree of specialization of the code fragment. Frequently appearing fragments are deemed less relevant, as we are seeking to specialize the GP towards this particular task. Once a fragment has been obtained, we begin a GP process with the constraint that all programs in the population must contain this particular code fragment. This restricts program space and thus improves the GP's performance. There is no requirement for the population members to make use of the code. As we use linear genetic programming algorithm, the code fragment could simply be present as introns and not contribute to the program's current behavior. We found this to be superior to forcing it to always be present in output relevant code. In essence, the code fragment can remain dormant until the GP can assemble the program sufficiently to make use of it.